This is my lab 2 report. So, quick introduction on what we did. The purpose of the lab is to record some projectile motion in real life. For my group, that was a balled up paper ball. Then use that data to create two computational models. One computational model would take the initial conditions of the paper ball and show how the paper ball would move through space if only gravity was acting on it. And then the second model was gravity and drag, and then we would compare the results. And what we found was that the computational model that took drag into account was much more similar to the observed data. And that makes sense because the main forces acting on the paper ball in real life are gravity and drag. So this is just a quick look. Right here we kind of have the real life data that we tracked, and this is what it looks like in like CSV form. And yeah, so how we actually created that model. So we took this original data right here, and from that we first we estimated a mass of the ball, right? We're like, the mass of the ball, we don't know exactly, but it's going to be like about 0.003 kilograms, right? It's pretty light. We used that original data that I just showed a second ago to get the starting original position and the ball's average velocity. And then we just had to estimate the drag force, but this value of 0.002 was pretty valid for our group. Next, we calculate the ball's position over time using the position update formula as given by Newton's second law. So notice the formula requires a velocity, and velocity of course uses a net force, right? So gravity is of course calculated as it's a vector, 0, negative mg0, and then drag also is calculated as negative b, the magnitude of the velocity squared, and then the direction of the velocity. And then fnet is like gravity plus drag, or just gravity depending on which model. So obviously this is the first computational model of just gravity. And yeah, you use this fnet to calculate the velocity and use that velocity to calculate the ball's position over some delta t. So what we found, so blue is the observed data, red is the computational model that had gravity and drag, and then yellow is the computational model that had just gravity without drag. And you'll see that the blue and the red one match up pretty closely. I mean, it gets like to a point like in this little midsection area where you can't even see the blue dots anymore, and that's just because the red and the blue line up pretty closely. And of course what this means is that the models are pretty close to each other. The yellow line, the model that only has the gravity without drag, drops off really quick, which makes sense, right? If there's no drag, obviously your projectile is going to fall faster. Meanwhile, the blue and the red lines take a longer time to hit the ground, which is x equals 0, which is kind of this horizontal line right here. And that's just because, again, drag is going to just delay how long it takes for your object to fall. So what are some potential errors? The drag constant is off. Like I mentioned earlier, we had to estimate what this b value is. We used 0.002. The mass of the paper ball might be off. Again, we had to estimate how much the paper ball weighed, and that's just the ball's mass right here, and we did 0.003 kilograms. And then the final potential error is the tracker video data isn't perfectly precise. I mean, the video is kind of blurry, and you just kind of have to estimate where the ball is per each frame. And then finally, the required questions. So what if the object was initially thrown straight up with the same initial speed? Would it take the object longer to reach the ground, same amount of time, or shorter? And if you think about it, the ball would actually take longer if you threw it straight up, right? In the first experiment, the actual experiment, the parabolic throw, less of the speed is upward, right? So you have a lot of kind of horizontal speed. So the ball starts falling sooner. If you were to throw the paper ball straight up, all of its speed would be upward. Then eventually the acceleration of gravity would have to bring that speed down to 0 and then start accelerating in the negative y direction. And of course that would just take more time. So yeah, in the first experiment, the actual experiment, um, the object hits the floor in a shorter time. Thank you all for listening, and thank you so much.